This is video number 4 for redoing the session on September 28 electrochemistry class. The discussion was on what happens at the interface between electrode and electrolyte. We saw that already, that in equilibrium, in electrolyte, if you have a redox reaction, the distribution of the reduced form is mimicking a Gaussian distribution in energy level, and the reduced form also mimicking a Gaussian distribution, but at a different level. So the average of these two would present the redox potential of the reaction in equilibrium. However, if we push the reaction to produce more reduced form of the material and consume more oxidized material, the average then would be different than what it used to be. And this is also explained by Nernst equation, as we know that the concentration plays a role in fixing the potential of the junction. So the question now is that how this is related to discussion of the electrode-electrolyte interface. We start now with just the metal electrolyte interface, and then we look at the semiconducting electrolyte interface. As I explained before, when we have a metal in an electrolyte, the very first thing that takes place is that the ions come to the surface, and that's a physical motion shielding the charge, and that may be sufficient to balancing the energy across the junction between electrode and electrolyte. However, that bringing ions so close to the surface of the electrode may affect the balance of the redox system that we have in the electrolyte. So having some ions so close to an electrode that can easily give electron or receive electron could change the balance of the redox reaction in a way to, for example, produce more reduced form of the ions and consume more oxidized form. If such a thing happens, practically it means that these sort of the potentials in the electrolyte side would be affected by the presence of the electrode. And what happens is practically the same way that we when we look at the metal and semiconductor, we believe that metal has such a huge amount of the charge in its volume that giving a little bit of the charge or receiving a little bit of charge is not affecting much of the energy structure of that. So the same story happens here. We can assume that the Fermi level of the metal is wherever it is, but that can force the reactions in the electrolyte to kind of go to a direction to change the redox potential, according to Nernst equation, to a different value to match up with the energy level in the electrolyte, in the electrode. So at the end, in equilibrium, as we expect, the energy level would be the same across the junction, but this has been achieved through changing the concentration of electrolyte to match it up. Again, it's not the only mechanism, it's one of the mechanisms that takes place. The other mechanism, as we looked at, is formation of the double layer. Well, when we look at the interface between the semiconducting and electrolyte, now the story could be a little bit different. The reason that the change is in electrolyte side when we have metal electrolyte interface is that metal is the hard material in terms of the energy. Hardly we can change the energy level of that, whereas electrolyte could be changed. So in the interface between the semiconducting and electrolyte interface, semiconductor is the soft material, and electrolyte, if the concentration of ions is at a high level, a few moles, then the effect of the energy matching would be more extended to the semiconductor part, and the electrolyte would stay as it is. So in a case like that, if we assume that the energy level of the electrolyte is not changing, but all the change would be on the semiconductor side, electrode as a semiconductor, then we can mimic this junction as a Schottky contact in which the electrolyte is serving as the metal part and the semiconductor is the semiconducting part. And therefore, what we get, it would be a sort of the band bending in the semiconductor, and not necessarily the concentration of the ions could be changed. It may stay as it was, however, a slight change may happen in the electrolyte as well. So knowing this, from this point on, we can analyze the situation for an electrolyte with a semiconducting electrode to a Schottky contact, and we can see that, for example, there's an energy barrier for the charge to move from semiconductor to electrolyte, and that produces a sort of the rectifying junction between the electrolyte if the material is semiconducting. What's the use of that? There could be other use such as Dyson solar cell. That's the discussion of this will be covered in next session. Also, I went through I jumped to almost the end of this sets of the slide, and I presented a couple of the figures from a publication that we have in Electrochemical Acta. It's about piezoelectric materials, zinc oxide, in particular zinc oxide nanowires, that we use it in an electrochemical system. So the purpose of this research was to use electrochemical method for finding the depletion width in a zinc oxide nanowire. So practically the same way that we just reviewed, an interface between a zinc oxide as a semiconductor and electrolyte was made, and we look at the capacitance of such a Schottky contact between the two materials, and by monitoring the change of the capacitance in the zinc oxide, we could figure out the depth of the depletion region inside the zinc oxide. So the point of this study, relevant to the subject of the course, is that electrochemistry and electrochemical method can be used for characterizing semiconductors. If we know the theory behind that we can kind of model electrolyte semiconducting electrode as a Schottky contact, so we can use the same theory as we had before for Schottky contacts between the metal semiconductors to explain the property of the junction. I hope this redo would serve as a good kind of explanation for what's missed, and if there's any further question, I would be happy to answer. Thank you so much.